Hello, my friends. Today we are going to be talking about energy stored by a capacitor. So, we know that a capacitor is a very important device in analog electronic circuits. So, when you search around, you'll find that most of the electrolytic capacitors look like this. This is an electrolytic, and it is polarized, meaning that when you're connecting it, you must be aware of which one is positive, which one is negative. The positive is the longer one, the longer leg. Then this is negative, which is a shorter leg. So you must make sure that the positive is connected to the positive of the battery terminal and the negative is connected to the negative terminal of the battery. Now let's discuss uh, the energy stored. So we have a capacitor symbolized by two plates, okay, that are connected to a battery energy source. So let's assume we have voltage V across there, or the potential difference across the battery terminals is that. And this is responsible for creating an electric field across the capacitor plates. So let us assume that we are going to be transferring charges from this plate to this plate so that when it is fully charged, we have a total charge Q. So let's say work done in moving a small charge dq across the capacitor plates due to the potential difference of the battery. So that small work done, let it be the W. It is going to be equivalent to V, okay, which is the potential difference across the battery, then times the charge moved. So let me write it in words so that you can always remember it. So what we are going to do is to say the work done is equal to the potential difference times the charge moved. This is actually the same as if we were doing a small work in lifting a mass through gravitational field. And if you look at it closely, you will find that it is analogous to this because it would be a smaller mass, which is actually representing this smaller charge moved, times the acceleration due to gravity, and obviously times h. So if we are talking about lifting a mass, so let's look at the analogy of lifting a mass. So the work done, this is through a gravitational field. So the work done would actually be the G times H, okay, then multiplied by the smaller work done. And here, the smaller work done, so this is a smaller mass dm. Now coming back to here, even if this now you forget about it, coming back here, we shall say the smaller work done will equal to the potential difference, which is V, now times what? Times the Q, which is the small charge moved. Because in charging, we are moving small charges, tiny charges, very tiny charges from this plate to this plate, this plate to this plate, until it is fully charged to Q. So that means if we want the total work done, this is going to be integrating V dq from 0 to Q, because this is the total charge. But we know that V is equivalent to Q out of C. So let us say this is going to be Q out of C, since we are going to be integrating with respect to this small q. So therefore, the work done will be integrating from 0 to Q of Q out of C with respect to Q. So integration, we add the powers here, we increase the power by 1 and divide by the new power. So this becomes Q squared divided by 2C, and then we just have to substitute in the limits. And what does that become? The work done becomes Q squared out of 2C, whereby Q is the charge. Actually, let us say total charge in coulombs, and then this is coulombs. And then C is the capacitance, I mean this C, capacitance of the capacitor. We say the capacitance of the capacitor is the ability of the capacitor to carry energy. So capacitance of the capacitor, and this is in farads. So we can say energy E of the capacitor becomes Q squared out of 2C. If we wanted to express it in terms of also V, not Q inclusive, for example, if you're given voltage, then we know that Q is equal to CV. So what does that mean? I'll just bring it here, and our energy becomes C squared V squared divided by 2C. So what does that mean? This gives you this one going with this square, and you'll have CV squared out of 2. Therefore, the energy stored by a capacitor will always be E equivalent to a half CV squared, or a half Q squared out of C. So whichever formula you have, and whichever quantities or parameters you have, you are able to calculate energy. If you are given capacitance and you have voltage, you can compute energy. If you have a charge and capacitance, you can still compute energy. Let's take an example. So someone can ask you, what is the energy stored in a capacitor with capacitance of, let's say, 30 microfarads and potential difference of, for example, maybe 50 volts. So that means you can look at the solution as from E equivalent to, what do we have here? We have capacitance and voltage. So this will be a half CV squared. And this is going to be 1 out of 2 times, this is 30 times 10 power negative what? This is times 10 power negative 6 to convert it to farads. Yes. Then we multiply by 50 squared. So the energy stored here will be a half times 0.075, and this is 0.0375 joules. Remember, energy is measured in joules. So if we talk about if charge moved is let us say 30 coulombs, and capacitance is, for example, 100 microfarads, then what is the energy stored? So this means I'll just say from E equivalent to a half Q squared out of C. This is going to be a half times 30 coulombs squared divided by C, which is 100 times 10 power negative 6. So we'll have 30 squared divided by 2, then divided by 100 exponent negative 6. Remember, I am using my calculator. So the energy here is actually equivalent to 4.5 times 10 power 6 joules. So that is the energy stored by a capacitor. And this is very important when you're designing circuits, when you're sizing your capacitor that you need in your circuit, then this is very important for you to go through. Thank you. Remember to subscribe, like, and share the video.